So I actually realized that there's a nice way to maybe summarize the whole class, which is the point of, the whole point of the class, and like exams that are like finalized to show your knowledge of said class. And what I've settled on is, do you remember internal energy from last semester, 1/2 kBT or 1/2 RT times degrees of freedom? And you may have also recalled that CV, heat capacity, was the change in U with respect to T at constant V. And so for something like argon, that was like 3/2 RT or kBT. So I'm going to use RT because I'm talking microscopic. 3/2 R. And sure enough, if you look up the heat capacity of argon gas at room temperature, remember these are temperature dependent, you would see 3/2 R. Now remember, degrees of freedom were temperature dependent. I told you that. If you freeze the damn thing, it can't translate in X, Y, and Z like a gas because it ain't a gas. Once it is a gas, it can rotate into and methane can rotate differently because dimensionality. You remember that? But I said you could not do vibration. Vibration was not allowed. And the reason was, I said in 346, you were going to do quantum mechanics and you were going to learn that vibration comes in discrete jumps, the energy of which is way greater than kBT. So if you can't store energy into vibration, you can't take it out. So what the heck is the point? It has no thermodynamic value if it can't be used to store or take out said energy at a later time. So it doesn't contribute to heat capacity. Remember, heat capacity is I'm throwing in energy and changing the temperature, but this doesn't do anything. You can throw energy at it at around room temperature. You can throw in thermal energy, but it won't take it. So it's just, it might as well just not be there, ergo doesn't contribute to the degrees of freedom. Okay, now we can prove it. And that's the point of this part, where what I would do is look at those energies and plug them into, and here is the question, what would I plug them into? What kind of mathematical analysis would I plug in the quantum energy levels to calculate the probability that thermal population, that I've got these states populated? Schrodinger equation gives me the energy levels, and I plug those into, that's the question. What? Heard one of you say it. Maxwell-Boltzmann. Remember, Maxwell-Boltzmann tells you the probability of having a certain energy. Remember that? Maxwell-Boltzmann said, this is the probability that something has nature parceled out this amount of energy. Well, if it's parceled out that amount of energy, that's the remember, it's the probability of having this amount of energy versus that amount of energy versus that amount of energy. That would be the same thing as the population. So if it's 10%, 5%, that means 10%, 10% odds that something has this energy, that means the population of gas has that much energy. And so I'd be talking about something that can vibrate, of course, so this is N2 or methane. So again, if the Boltzmann distribution says nature at KT, at room temperature, with KT energy, if something has a 10% probability of having this energy, then that's the population of things in the first vibrational excited state. Ground state, first vibrational excited state, second, third, yada, yada, yada. Okay, my thesis is, what I told you back then, is that everything is basically in the ground state, nothing's in the first excited state, let alone second or third, that's even worse. That is what I told you, that's what this means. That these levels are so high, all the molecules are in the ground state, they just sit there, they don't do anything, so they don't contribute to heat capacity. All of this. Now, we can prove it. So let's go about it. Right now, remember at the beginning of this class, and you may also, some of you who've looked at your homework may be recognizing that I'm answering one of your questions. We have done quantum vibration, so we know all the energy levels. Now, there's another thing about this. Okay, so here we go. Let me write down all the formulas. You've seen them before, but just in case. Okay, so the frequency, there's a little bit of an issue here whether I'm talking about angular frequency or there's a difference between angular frequency and frequency. there is a square root of the force constant. You learn this in mechanics when you learn springs. Square root of the force constant divided by the reduced mass of the spring. Now the reduced mass, of course, for N2 will of course be the mass of one atom, mass of the second atom. Of course, if I'm talking N2, it's the same thing. If I'm talking CO gas, then that's actually a little more legit. Okay, again, this is why it took me all morning. It took me a while to find all of these things. 1193, that's a Newton per meter. That's a spring constant for N2. Okay, so there you go. And so anyway, I was Googling all this stuff, and I found, I know this, it was in class, I remember. I was able to Google that. Of course, I know how to translate AMUs to kilograms. Remember, kilograms is standard SI mass. Okay, and then I wanted to make sure this made sense, so then I calculated for N2, so the spectroscopic observable isn't the frequency, it's the angular frequency. That's what you observe in an experiment. So I put all that together, and I found that this was 5. I've got two sets of values here, by the way. 5.099 times 10 to the 13 hertz. Remember, this is a frequency, so that's a 1 over second, and that 1 over a second is a hertz. Now, I can divide that by the speed of light to get wave numbers, because any of you who know anything about infrared spectroscopy, especially the chemists who are doing this in PChem lab, know that you can turn this into wave numbers. Vibrational spectroscopy, FTIR spectroscopy, is done in wave numbers. You typically look at, I wrote down the wrong number, sorry, again, I've got two sets of numbers, sorry about that, sorry. The reason I recognize I just wrote down the wrong number is because infrared spectroscopy varies from about 200 to about 3,000 wave numbers, where 3,000 is H2. Except that H2 doesn't have a dipole moment, heads up. N2, H2, I2, those things, they actually aren't IR active, and you know that because you plug in the vibrational wave functions and the dipole operator, and you get 0. It takes heterodiatomic, it takes CO. CO is IR active. And so anyway, and the reason is because when you plug in those wave functions in the dipole operator, those vibrational wave functions, then you don't get 0. So anyway, okay, now this is about, despite the fact that I cannot measure the IR spectrum of N2, there are other ways to figure it out, and this is about right. So this makes sense. Okay, now that I know this, I've got, I've got everything, I've got all the parameters, and the numbers are good, so I Googled them, but so I thought to double check on it. It looks good. I should be able to do this. Okay, hopefully you recall that the probability of observing a certain energy, now notice I'm having to blend in our Maxwell-Boltzmann learnings with the quantum learnings. I'm doing that by adding the vibrational quantum number, this little, let's call it V, it's V, whatever, it's V. I'm using a quantum number, and that of course is e to the minus energy of that state over kDT, and I'm going to use, for the most part, room temperature, and kD is kD, gas constant divided by Avogadro's number, in case you forgot. There we go. Okay, now, this bottom part is the sum over all states. And before, remember, I plugged in energy was 1/2 mv squared, and then the sum could turn, there were 3 of them because of x, y, z. I was able to turn the sum into an integral, yada, yada, yada. This was only 2 months ago, by the way. Now, when it comes to vibration, it's actually kind of easier. Sometimes maybe I should teach Maxwell-Boltzmann at the end of quantum, not the beginning. I'm not sure. Anyway, it turns out that quantum numbers go from 0, 1, 2, yada, 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 to infinity. Also, you see what I got to do? How do this guy, I know what the energies are. Look, I just figured them out. Wave number is technically a unit of energy. I can express kBT in units of wave numbers, by the way. It's about 206 at room temperature. So I got this guy hacked. Now, what do I do about that? What do you think? look up an identity, right? I just have to figure out what the formula is. Here, I'll keep working down. So I just got to plug in. I got to plug in the energy, which is just what I wrote. And then what I did was, which is literally what I did was, Googled some formulas for sums of exponentials, because that's a sum of an exponential. Now the reason that I can find a closed solution, that means a solution, is because of the way that n goes from 0 to 1 to 2 to 3 in a regular way. Here, let me write that down. So when it comes to the Boltzmann distribution, when you get past velocity, Maxwell-Boltzmann, remember that when I say Maxwell-Boltzmann, I'm talking about velocity. Boltzmann is just that guy, that thing right there, and that can be applied to whatever. Maxwell-Boltzmann is when we're talking specifically velocity of a gas. Okay, when it comes to solving Boltzmann this and that, really it's all about the normalization. If you can get that, you're home free. The top part, that's never a problem. And you should always be able to figure that out. The bottom part's the problem. Okay, so what's the bottom part? Okay, so again, I'm just going to plug in whatever the heck I've got. I've got, okay, now I'm going to do something a little funky here. I am going to change the formula for energy. So what it is it's the quantum number plus a half. What I've done is I've eliminated that. I've eliminated that in the expression for energy. And I can get away with that for two reasons. One is that I take the parabola, which is centered at 0, and has rungs. Remember that there's this 0 point energy thing. That half is the 0 point energy. And what I've done is I've just shifted it down. I just shifted it down. And so that the ground state is 0 energy. That's all I did. That doesn't do anything. If you shift energies up and down, it doesn't matter. Remember, the only thing that matters are relative energies. So that's why that's valid. Energies are relative. So if I shift them all up and down and keep track of that, which is actually easy in this case because I simplified the equation for energy, then I'm okay. Now here's another reason why I can get away with this. It turns out that you can express, let's say I just didn't do this. Let's say I didn't do this because I feel like what I'm saying right now is too confusing, I just didn't do it. What you end up with is you end up with just a term that multiplies, let me write this down. Let's say I didn't get rid of it. What you end up with is, you end up with this extra term. Guess what? It's a constant and it appears on the top and the bottom, right? It's energy. It'll appear on the top and the bottom and therefore just cancels out. So I don't need it. Now the reason I'm canceling out is because that makes this a hell of a lot easier. Because when I Googled identities, and you've seen this before, it turns out that there are identities for sums. And I found this one. It's incredibly easy. Sorry. It's that. Again, that's an identity, and it only works because this n goes 0, 1, 2, ... If it does anything else, it's not, I don't know what it is. But anyway, so it has the solution. Okay, so when I apply that to this thing, I'll just write it again. Notice it's basically the same. E to the minus h bar. I wrote it slightly differently. Sorry. It's actually quite simple. It ends up being 1 over 1 minus e. Yeah, there we go. End up being just. Let me write it a little bit neater. There we go. Ends up being really simple. Okay, so there you go. All right, therefore, the probability that N2 is in the ground state, once you get all the numbers all worked out, it ends up being, now the neat thing is, is that the energy, I look at the top part of my Boltzmann distribution, e to the energy, if I'm going to do, the ground state, because of the way I redefine the potential energy surface, the energy of the ground state is 0. And you see, again, it is way easier to shift this down a bit because it doesn't matter, it just makes everything way easier. And this sum ends up being, again, I plug in numbers, 1.00027. And that is, of course, a very big number, that's very close to 100%. There you go. Overwhelmingly, nitrogen is in the ground vibrational state. Okay, let's do first excited state. First state, excited state. First state's the ground state. Now I realize that gets kind of confusing, that I can say the first state's the ground state. I need to say first excited state. So that's this, and that ends up being, did I write it all out? E to the, so it's not 0, it ends up being 0.27, okay, incredibly small. So there you go. Just tiny, tiny, tiny. So overwhelmingly, these are in the ground state. Now, if you are doing heat capacity measurements, remember that you're inherently changing the temperature. You're changing the temperature because that's what a heat capacity measurement is. How much energy do you have to change the temperature? Now, the point of this is that the reason this doesn't contribute is if you recalculate this at 300, 400 degrees, the numbers just don't change. They change, but it's really minuscule. And that means that, again, it's a dumbbell. It's not responding. So let me show you, though, what happens is if N2 is at 1,000 degrees. See, now you can calculate this. So again, heat capacity is a measure. It is how much energy does it take to change temperature. And what you're finding is that these populations, you can do this on your own if you feel like, these populations just aren't changing. But now if you go hot enough, eventually, yes, eventually it will change. So if you're at 1,000 degrees, the probability of being in the ground state drops. It drops to 84%. So you see, probably in the first excited state, is it doesn't, of course, add up to 100% because there's some very small probability for being in the second excited state, yada, yada, yada. What you're seeing now is the addition of thermal energy actually going into vibrational modes. But you have to get it really freaking hot, and the reason is that just the numbers work out that way. Now, let me show you this as well, and then I'll give one more example. If you look at the heat capacity of N2, I can't remember if this is CP or CD. When you look at room temperature, 298, about 800. And these are in Kelvin, of course. About 1,600. And then like around 4,800. I don't know if I'm really on the scale here. You get 29.2. If you add R to that, meaning that you've added, so remember, if you add a degree of freedom, that being vibration, you're going to add an R according to the equal partition theorem of heat capacity. So it turns out that you're down at 29.2. Around 800 it starts to kick up. And then when you hit about 4,000 degrees, at that point, you have unencumbered ability to populate higher vibrational states. And that means that the heat capacity raises. And remember what that means is it takes more energy to heat this up. The ability to populate vibration is like a loss. You want it to get hot, but instead what you're doing is you're making it vibrate more. You don't really want that. When you heat a gas, you want it to get hot. But when you get it too hot and the vibration modes start getting populated, then that sucks. It's like you're losing it. Well, not much you can do about it based on what I just calculated. So there you go. Okay, now if you do, here's another example. I2. I2, and these are the numbers I was accidentally writing before, has a much smaller spring constant. Yes, Newton per meter is a kilogram per second squared, by the way. Makes a little bit more sense when you look at this. Its reduced mass is way higher. Wait a minute. I hope I wrote this down before I was obviously. I was getting these confused between N2 and I2 because I have them both right in front of me. The angular frequency is, I'll change the video if I screw it up. I don't know what I just wrote. This is 228. Okay, so again, I Googled the spring constant of I2. I looked at its reduced mass. I just looked at iodine and divided it by 2. Made certain that the frequency of vibration in wave numbers is around 228. Now remember I said KT at room temperature is about 206 wave numbers. Wave number is a legit unit of energy. Now that those are so close, guess what? When you do all the probabilities, probability I2 is in the ground state at room temperature. I didn't even do this at higher temperature. It's actually 66.8%. And first excited state, of course, is close to summing this up to 100, but not quite, because it has a 7% chance of being in the third excited state, so there you go. So when I mentioned to you last semester that there's this little funniness about heat capacity and vibration, I mentioned to you this is sort of true because some things have such weak bonds they actually do absorb energy, and I was talking specifically about iodine. Iodine has about the weakest bond that's known to exist. A weak bond, like after you did on that last test, has a low frequency, that's low energy, and that means the Boltzmann distribution may actually kick in and allow this thing to absorb energy. Okay. Anyway, I just wanted to point out that these types of questions mix quantum in your Maxwell-Boltzmann, right? All you got to do is have some energy equation and an identity, and you can do the last question. Then you can do any questions that you might have on an exam, right? And then, like I say, I kind of am very interested in this because it allows you to mix what you've learned at the first part of the class with the second part. It's a little bit hard. I mean, there was a lot of that in last semester until we got to like solutions and blah, blah, blah. Okay, last thing I wanted to show you here, and we should break, I got to go practice my Chinese. There's this one, and actually I'll stick around to answer homework questions if there's any homework questions. I should have asked about that first, but I can stick around if you have homework questions. But I want to show you one other thing. So you may be thinking, like, I'm going to come up with some example problem, and maybe you'll see that again. I might be thinking that. Let's do hydrogen atoms. What's the probability at room temperature that hydrogen atoms are in their ground state? Now you can imagine that would be very high because the energy to excite an I2 is not much because it's a big, heavy, floppy, dead bat. All right? Now, so it doesn't take much energy to get it to vibrate more. How much energy does it take, it's like thermal energy, let's say, to excite an electron in a hydrogen atom? Is it large or small, based on last lecture? Extraordinarily large, right. So remember I said you can do it spectroscopically with 91 nanometer light, which is like mega lethal X-ray type of light. So no, I mean you can do it. It's just high energy, right? Infrared light to excite I2 is way less energy than 91 nanometers, which is instant death light. Okay, so in other words, you know that I should not be exciting electrons based on heat, at least not at room temperature. I want to point out one thing that's kind of neat though. So I'm going to write out the Boltzmann distribution, but I'm going to add something you haven't seen before. And energy, of course, is what I wrote before, but let me write it down again. Energy is, we like to express, now I'm going to do the quantum bit, right? Now the whole point of quantum mechanics is that I get all the energies. And because I have them as a function of quantum number, that's what makes these Boltzmann deals actually really easy, because it's a sum. It'd be a sum of states, and the states are well defined by quantum numbers, right? You see how these mesh? Now, it turns out that, and I'm going to start using different units, 13.6 eV per n squared. Now remember, on a per molar basis, this is like mind-boggling, right? On a joule, on a single particle level, this is small. Now again, 10 to the minus 18 joules is small until you multiply it by Avogadro's number, and then it becomes bombastically large. Okay, now you may notice that I've added something here that you haven't seen before. This is a degeneracy. You haven't seen this before because, for one, we kind of stopped doing Maxwell-Boltzmann because we weren't doing it anymore. And when we were doing Maxwell-Boltzmann, we didn't have any degeneracy. So remember that this was the sum of energy levels. When you do quantum, you discover degeneracies, right? Remember we ran into the first degeneracy in a particle in a 2 or 3D box, and then we ran into them with rigid rotor. You can have m plus 1 equals to m minus 1, the same energy. We now run into them with hydrogen atom. We now know that a 2s has the same energy as a 2p, x, y, and z. Remember that the energy depends on the n quantum number, not the L. So therefore, the energy of a 2s state is the same as a p, x, y, or z. So that means that the degeneracy for the 2 state is 4. 1s and 3 p's, that's 4. If I have n equals 3, what's the degeneracy? Now for one, I've told you because it's right there. So what is it? 9, because 3 squared is 9. So that's one way to answer it. Or
3s.
Right. There's
3p.
3s, 3 for the p's, that's 4, and then there's 5
for the d.
5 d's, right? That's 9. Okay, so I just want to point out that there is this degeneracy factor you hadn't seen before, but remember I told you at the very beginning that these Maxwell-Boltzmann deals, really Boltzmann because it's not gases, is just the sum of the energies. But you have to include degeneracies, right? So it just didn't come up before. Okay, now here's a funky thing. When it comes to hydrogen atom, this is kind of cool. All right, so the energy is negative already, which is a bit of a problem. And it's m squared e to the E0 over n squared. So forget all the kb's and all the constants. Okay, so it works like this. Notice a couple things. I'm not putting in some constants. I'm not putting in kbt, whatever. Did I just forget the minus sign? No, the energies are negative. Did I delete that? I deleted it. Anyway, right. The energies are negative for the hydrogen atom. Guess what this is equal to? It's infinity. It's a non-convergent series. You ran into that when you learned a series at some point. Some series don't converge. This is one of them. The normalizer is infinity. So what do we do? So is this a big mistake? Quantum mechanics could be wrong, I didn't do the math wrong, trust me, I looked that up a couple of places. This series, e to the n squared e to the 1 over n squared is a non-convergent series. The constants don't fix any, I know I didn't write over kBt, that doesn't fix it, nothing fixes it, it's infinity. And that means the probability of everything is 0, which is wrong, right? Heads up, by the way, this actually should be 1. This really ought to be the number 1, just like you saw with N2. When everything is in the ground state, your normalizer really needs to be close to 1. It certainly should not be infinity. That's the exact opposite. Anyone have a solution? Because it's really weird. So anyway, the point of this is I didn't do the math wrong, but this is a gigantic, here, just to plug out, this is a gigantic error. This is a gigantic error. And here's the solution that somebody came up with a long time ago. On your homework, I alluded to this a little bit. I ended up taking the question off and putting it as an appendix. Regardless, I'm kind of rambling. On your homework, you're doing this. Right? Go ahead. You know what? Whatever. That's the answer. I just answered your homework. Now, you still have to work it, okay? It doesn't matter if you give me the answer. Okay. Now, on the appendix, I gave you the average for the 2s. And by the way, if you divide it by the 1s, I don't remember it off the top of my head, it's 4. Here's a hint. 4A not. No, sorry, the ratio is 4. Ratio is 4. It turns out that the hydrogen atom grows in the excited state. So if I have hydrogen in a 1s state, it lives about a Bohr. It's about a Bohr wide. A Bohr is a very small number, half an angstrom. That's a tiny, tiny, tiny little thing. If it goes into the excited state, it gets wider. And again, I have you do this on your homework, and then I show you how to do this. You can see the ratio is 4. And it turns out that the hydrogen atom, if it gets into the excited state, however that happens, it gets bigger. If you talk about N as high as around 10,000, I believe, I have the number around here somewhere, whatever. If you're talking about N around 10,000, the hydrogen atom is about a meter. Question?
When you think about it, it has to grow because it's already in the valence shell.
Well, I mean, it just, I don't know, it just is what it does. I mean, there's actually a more accurate way to think about that is to remember that, to remember this. Remember that these things have to be orthogonal. Solutions to wave functions that are solutions to an operator like the Hamiltonian, they're orthogonal. The only way you can do this thing has to grow. It kind of has to get out of, they have to get out of each other's way. That's actually kind of a more accurate way to think of this. So it has to grow, just simply has to get, they have to get out of each other's way. So, if you're doing this sum, you're talking about n going to infinity. How big is a hydrogen atom with an infinitely big n? Huh? It's infinitely big. How realistic is that? No. So, if the Great Turkey created a hydrogen atom in an empty universe all by itself, it would explode at the speed of light. I don't know what would happen, but then this would be true. But I have no idea what the consequences would be. But in this universe, solving this is stupid because the hydrogen atom can't do it. Any study of the hydrogen atom properties for which you're applying this is in a box probably no more than about half a meter. And so it can't do this. It can't grow without regard to the size of the container or the solar system or universe it's in. So there's actually a natural limit to this that doesn't allow the hydrogen atom to just grow without bumping into something. And that actually is what keeps that normalization from exploding to infinity. So anyway, so that's a funky one. It's a well-known problem in physical chemistry. You actually learn, this is one of the first things you learn as a grad student, and sometimes I show you that stuff because I think it's kind of neat. But what I kind of like about that as well, it shows that this stuff is practical. When your math does something that's like impossible, there's a practical solution. And anyway, that's it. So anyway, I wanted to show you that. With that, I got 5 minutes left. If you folks wanted to